Welcome to the next video, chapter 19. So you'll notice we skipped over section 19.7. So we'll do 19.8 first. This whole video will just be on this one section. We'll do 19.7 in the next video, the last video for chapter 19. And the reason for that is it's going to tie in pretty readily with the one video that we'll have for chapter 20. So you should probably plan on watching 19.7 and the chapter 20 video soon after one another because they're on a related topic. Okay, so this section is all about heat transfer mechanisms. In the previous video, we talked about heat, Q, and calorimetry, how Q relates to temperature. So in that video, we just said, oh, hold a flame up to a gas, and that's how you can warm it up. So in this, so that's one example, holding a flame next to something. That's one example of a heat transfer. But we want to generalize this concept and talk about all the different kinds of heat transfer mechanisms. So there's three in particular that we're going to cover: conduction, convection, and radiation. So for the first and the third one, we're going to have an equation describing the rate at which heat is transferred. So remember, energy per unit time is going to be a power. So it'll say how quickly heat is being transported. The question that we have, so really I could think of a couple different questions based on which heat transfer mechanism we're talking about. This question has to do with conduction. So if we had a steel rod and a copper rod that were welded together right at the midpoint, and the geometries of these were the same, so same length and same cross-sectional area. Suppose we wanted to know what the temperature would be right at the midpoint. So we already know, we have some idea that it should be somewhere between 100 degrees C and 0 degrees C in equilibrium. But knowing these properties of the metals, we should be able to be more quantitative with that. So we should be able to answer that. Okay, the first heat transfer mechanism that we're going to go over is conduction. And this is basically just a hot thing touching a cold thing. Hot touching cold. So to me, this is the most basic one of them. You know, so if you have hot water and cold water, you can, if you have anything connecting the two, so you can touch the hot and the cold, then energy in the form of heat is going to flow from the hot thing to the cold thing. So I'm not too worried about signs in equations that I'm going to write down, because it's understood that heat is just going to flow from the hot thing to the cold thing. So you know, you can always imagine taking the magnitude of these equations, and of course it'll flow from hot to cold. I want to motivate this equation right here. So maybe with this picture right here, so we have a hot thing and a cold thing and something in between, so some slab of material. This material is conducting heat across the temperature difference. So as long as it's uniform like this, it's going to be a very gradual transition from hot to cold. So if it's 100 degrees C on the left and 0 degrees C on the right here, the midpoint should be 50 degrees C, as long as the area doesn't change and the cross-sectional area of this slab doesn't change. And 1/4 of the way, it'll be 75 degrees C. 3/4 of the way, it'll be 25 degrees C. The actual material that this is made up of is going to say how quickly heat is going to be transferred. Okay, so despite the fact that the equilibrium temperatures we could probably guess, we still don't know how quickly energy is going from the hot to the cold thing, and it depends on the kind of material. So the kind of material is something that we need to account for. Also the area of the slab. So you would imagine if we had two slabs. So I want to motivate some terms in this equation. So the rate at which energy in the form of heat will flow. And remember, energy per unit time is a power. So you also see this power conduction. So this is energy per unit time flowing through a slab of material. So it makes sense. So first of all, there's going to be some constant here. So I'm going to leave space for that constant. It makes sense that it depends on the area of our slab. Right? If we had two of these slabs, then this heat transfer can operate through both of them relatively independently. Imagine the air is an insulator and that air doesn't affect anything. So it should depend on the area of the slab. It turns out that it's also going to inversely depend on the width of this thing. So imagine I had a slab connecting San Diego to the North Pole. Even though it might be a big difference in temperature, for the same area of slab, it's not going to transfer the energy as readily. So the longer this distance is, the less heat transfer there is. So this term sort of makes sense. This delta x, actually your book just calls it L, the length of the slab. So this will be the distance separating the hot and the cold region. And then of course it's going to depend on the temperature difference. So the bigger the temperature difference, the faster heat is going to flow. If they're at the same temperature, there's not going to be no energy in the form of heat flowing. So it depends on geometric factors right here, depends on the temperature difference, and then there's a constant to make this an equal sign right here rather than a proportionality. So this constant right here is called the thermal conductivity of your material. Thermal conductivity. Now, the units of this are going to be the SI units of this. Well, we need to cancel. So first of all, we need watts. We're going to be left over with watts just because we want a power. So at the end of this, we want watts. And then we need to cancel out all this other stuff. So an area divided by a length, meters squared divided by meters, gives you meters on the top. That means this constant is going to have meters on the bottom to cancel out. Once we multiply by area and divide by a length, we'll cancel those out. And then this delta T will be in Kelvin for SI units. So these thermal conductivities are numbers, and then the SI units, it will be the number in watts per. Now that's not millikelvin, so you got to be really careful reading that right there. W over mk. That's not millikelvin. That's meters times kelvins. So I'll definitely put a dot. I'll try and exaggerate it. Now this is saying how efficiently, how quickly energy is flowing across this thing. So diamond. Heat can flow very easily through diamond. And through metals, metals are good conductors of heat, electricity and heat for metals. For non-metals, it's harder to conduct energy in the form of heat through them. So you'll see, things like glass, it's a lot less. That's why we use glass for insulating our house rather than metal, right? The metal will just let the hot air right out of our homes in the wintertime. Glass, it's a lot harder for the heat to go through. Okay, so yeah, we've explained that equation. One other fact I want you to know is that so in equilibrium, the P is going to be the same across all of these surfaces. So if you have a hot thing, so it's hot, you connect a piece of metal here, and then you have cold right here. The rate, so the rate at which heat is going to flow will be constant throughout this rod in equilibrium. So in equilibrium, and I'm going to use this word in quotes because really, I guess suppose true equilibrium would be these two things being at the same temperature. But I mean, so I'm imagining these are heat reservoirs where this thing is so big that it's very hard to change the temperature of this. So imagine like the inside and the outside of a house. It's very hard to change the temperature of the outside or the inside of your house. So what winds up happening is that you get an equilibrium in here, and you get a constant flow rate. So the power that's flowing through here is equal to the power that's flowing through here. So in equilibrium, if I look at a total cross-section of this rod, and there's some power conduction, equilibrium P conduction is constant. If that weren't the case, then the temperatures would be changing. They'd be fluctuating here. So what happens is that a steady state flow is set up so that from hot to cold, it will be a gradual decrease in temperature from hot to cold. Now, the reason I mention this is it's relevant for this picture right here. So just in the question itself, it says, what's the temperature at the midpoint? Well, in order for it to have a well-defined temperature, we have to have reached some steady state. Okay, so what's going to help us here is we're going to relate the flow of heat here to the flow of heat here, and they have to be equal in order for there to be some well-defined temperature here. If they weren't equal, then the temperature at the midpoint would be changing. Okay, so the problem at the beginning. So the rate at which heat is flowing through the steel is equal to the rate at which the heat is flowing through the copper. So I'll use S for steel and C for copper. Okay, so just according to our formula right here, Ka over L delta T. This is K for steel, the cross-sectional area divided by the length of the steel, times delta T. And so delta T for the steel is going to be, so it's 100 degrees C here, and then we'll call this the midpoint, Tm, the temperature of the midpoint right there, or T middle. It'll be some middle temperature somewhere in between 100 degrees C and 0 degrees C. So the delta T, the magnitude of it, is going to be 100 degrees C minus Tm. Notice how that's a positive number because I already know that Tm is a number between 100 degrees C and 0 degrees C. Okay, so that's for the steel, and then for the copper, we have K copper times cross-sectional area of the copper divided by the length of the copper, and then this delta T has magnitude Tm minus 0 degrees C. And notice how the order in which I wrote these, I ensured that it's a positive number and a positive number. Remember, we automatically know that heat is flowing from hot to cold. So I just took account the signs that the delta T is going to be a positive here. Right? Definitely it's going to be the case that heat is flowing from left to right in this picture, from the 100 degrees C to the 0 degrees C. So knowing that the cross-sectional areas are equal, the lengths are equal, that really simplifies what's going on here. And we get Kc over Ks times Tm. And so notice how I wrote degree C rather than Kelvin. Remember, for equations that involve delta T, it doesn't matter whether you use Kelvin or degree C. Remember, it's the same thing. So I can go ahead and treat that 0, like it's 0, and that's fine. It looks like this is 100 degrees C minus Tm. So Tm, so 100 degrees C is equal to Tm times 1 plus Kc over Ks. And Tm is equal to 100 degrees C divided by 1 plus, now the ratio of those two thermal conductivity coefficients are 400 to 14. So 400 for copper and 14 for steel. So let's go ahead and divide this. 100 divided by 1 plus 400 over 14. Google tells me that this is only 3.38. Let's do 3.4 degrees C. Very, very small. So let's go back and try and think about why that's so small. It looks like it's a lot easier for heat to flow through copper. Right? The thermal conductivity here is 400 versus steel is only 14. So heat is very easily able to flow through here, which is why this temperature is a lot closer to 0 degrees C than 100 degrees C. Okay, if these two Ks were equal to each other, so instead of 14, 400, if it was 400 and 400, notice how this formula would give 100 degrees C divided by 2. It would be exactly the halfway point between those two temperatures. So in general, if you put two things next to each other, the thing with a higher thermal conductivity, the midpoint is going to be closer to that temperature. So you can imagine we can also play with the lengths here to be different. But the principle here that we use to solve this is the rates at which energy was going through the rods were the same in order to have an equilibrium temperature. Okay, so that's one of the three. The next one is convection. Now, convection is the most difficult quantitatively of the three, and for that reason, see how little is written about it in your book. There's no equations for it because the equations are notoriously hard. So I just want to give an example of this. So you have heat. You have your house. Well, none of us can afford a house in San Diego, but imagine you could afford a house. And let's just say that this is the walls. So we're going to focus just on the walls of your house. So this is the inside of your house. And let's say this is in the summer, where the inside of your house is really cool, and it's hot outside. Okay, so this is the outside of your house. Okay, now the air in here. Okay, so what goes on with air in here? So we're not talking about thermal conductivity just straight across. I suppose it would be going from hot to cold. So air actually does have a thermal conductivity. So notice it right here, but it's not very big, right? So if it's just air and it's just conductivity, not much heat flows. The main way that heat flows in the walls of your house is that the air here is going to warm up. So this air warms up and it moves, because warm air is less dense than cold air, the hot air there moves upwards, and the air here next to the cool inside is going to move down. The cool air is going to be more dense, so it moves down. And so what winds up happening is these currents are set up called convection currents. So this right here is called a convection current. So convection is heat flow because of currents set up in fluids. So convection is a phenomenon that happens in fluids. And actually, because of this, it's better to replace the walls of your house with styrofoam rather than leave it with air. So notice right here on the table on the left, the thermal conductivity of styrofoam is greater than air. So you might think it's silly to fill the walls of your home with styrofoam because it's just going to be worse in terms of conductivity, but it completely wipes out any convection currents that could be set up. And that's actually the main source of conduction. Sorry, I shouldn't say conduction, right? That's the main heat transfer mechanism between the outside and the inside of your house. So styrofoam will completely kill that. Okay, so other than knowing this qualitatively, you're not really responsible, and it's just notoriously difficult. You can imagine that the currents get pretty chaotic and difficult to describe mathematically. So if you're, a mechanical engineer, you'll take a whole classes on fluids trying to describe this phenomenon. Okay, the last one that we want to talk about is radiation. So to quickly sum up radiation, what that is, it's that any object at any temperature, objects glow. So this is more obvious. So you might think of this as obvious when you heat up something. So you heat up a fire poker until it gets red hot, right? It's glowing red hot. So you don't see an object glowing until it gets hot enough that it's glowing at visible frequencies. So it turns out that how hot an object is related to the part of the E&M spectrum where it emits, but actually everything is glowing. Human beings are glowing at room temperature. So you just have a person right here. So just at room temp, at room temperature, this person is glowing. Now they're glowing in the infrared, it's part of the spectrum. This person is glowing. Whether they're happy or sad, they're glowing. They're glowing in the infrared part of the E&M spectrum. So infrared at room temperature. Right? They're not burning red hot. Right? And actually, this dependence on temperature is very, very, very strong. So this equation right here, which talks about how quickly objects give off energy in the form of radiation, is strongly dependent on temperature. So let me write down this equation. So this is power, radiation, power given off by radiation, or dq dt. So there's going to be a couple constants. Let me hold off on those. And then a times t to the fourth. So the a is the surface area of your object, surface area. So the person has some surface area, maybe 0.1 square meter, order of magnitude 0.1 square meter or 1 square meter. The T is temperature, and this has to be absolute temperature. So notice how this is not a delta T, this is just a T. So you have to use an absolute temperature scale. You cannot plug in degree C for this formula. You can't plug in degree Fahrenheit here. You have to use Kelvin, or really that's the main absolute temperature scale we use. So the constants that we have here, so E is something called, E is related to how efficiently the object gets rid of radiation. So E is a number between 0 and 1. This is something called the emissivity of the object. So it says a measure of how effectively it radiates. So by the way, we use this equation in astronomy all the time, and it's a very good approximation to say that objects have E equals 1. So if you're not told anything about the emissivity of an object, it's a good approximation to say that it's just equal to 1. A perfect black body has emissivity equal to 1. It turns out, like I was saying before, it turns out that's a really good approximation for something like the sun. For the sun, you can just plug in E equals 1 and it matches up really well. So this depends on a lot of factors. Just colors, different colors will have different emissivities depending on how efficiently it absorbs and emits radiation. The last thing I want to talk about is this sigma right here, and this is just a constant, just a number, and this is going to include all the units to make this thing work out. And so by the way, so sigma is equal to some number, and then the units have to be, again, watts on the top is going to be left over for a power, and we need to divide by meters squared to get rid of that area, and then Kelvin to the fourth to get rid of that absolute temperature. So that number in SI units, as you'll see on the left, is 5.67 times 10 to the minus 8. This one's easy to remember, right? 5, 6, 7, 8. You just have to remember that minus sign. This is called the Stefan-Boltzmann constant, as we see on the left right here. Okay, and again, a note in the book. This must be in kelvins for the temperature. The book mentions objects not only emit radiation, but they absorb radiation. So a lot of times you have to use this formula twice. So when I wrote this down, I had in mind an object emitting radiation, emitting energy in the form of heat. And it's governed by this equation where T is the temperature of the body. So T is the temperature of the person's skin. That's what would appear there. The person is also absorbing energy in the form of radiation, and that depends on the background temperature of the electromagnetic radiation hitting the person. So if we're at room temperature, then we can assume that that's room temperature, and that's exactly what this equation is summing up right here. So this equation has two terms. There's a positive term and a negative term. So it looks like the T naught is probably the background one. So see how the environment is at temperature T naught. So this person, the dq dt is how much energy in the form of heat the object is radiating away. So by the way, this is a different sign convention than what we've been using this chapter, right? Normally Q is positive if energy flows into the system. This is not following that convention. This is saying that there's two terms, the temperature of the object and the temperature of the surroundings, and it's the difference in these T to the fourth. So obviously the net is going to depend on which is hotter, the object or the environment. Okay, so this is So the Earth sets up a equilibrium temperature with the sun. So energy in is approximately equal to energy out, and that controls the temperature of the Earth. So if you do that, you get a number that's about 30 degrees less than what our actual temperature is, and the reason for that is the Earth is able to trap some of this energy that it's trying to radiate away via greenhouse gases, the greenhouse effect. So your book talks about that a little bit. But to first approximation, this is what's going on with how the Earth gets rid of its energy. It's via radiation, right? The Earth's not touching anything. There's a vacuum surrounding the Earth, so it's not through convection or conduction. It's definitely through radiation. And then your book also talks about evaporation. So they don't give any formulas for that. They just mention, oh, by the way, this is the way your body cools down is often through evaporation. So water has a high specific heat. It's able to carry away energy pretty effectively. So evaporation and just warming up the water in your body. Yeah, that's it. Those are the 3 heat transfer mechanisms: radiation, convection, and conduction, and the 2 formulas you need to know associated with it.